Okay, this is experiment number 10, entropy, Gibbs free energy, and the reaction quotient. The purpose is to find the change in entropy for dissolving sodium nitrate and to find the reaction quotient known as Q for dissolving some calcium chloride. This is a fast lab to perform, but involves the most calculations we'll be doing all year. I'll be asking for 11 calculations at the end. Let's make some predictions. Since dissolving something is analogous to a decomposition reaction, one thing turning into more than one thing, in this case two, we can predict that this is an entropically favorable reaction. In other words, we should get a positive value for this. It still may only be in the on the order of joules per mole Kelvin rather than kilojoules, meaning that free energy units are typically far larger than entropy, but it's a number that we can calculate. The reaction quotient, capital Q, for calcium chloride is shown, the reaction shown here. Once again, it's simply dissolving. And you might be able to try to make some predictions about what that might be, but be aware that as long as you perform the calculation right, it plays no role in the accuracy part of today's lab. On the other hand, the entropy changes, try to get this as precise as you can, because that's where your accuracy grade will be coming from. Now, in the pre-lab, we asked you to calculate the standard entropy and free energy change values for dissolving calcium chloride. The way you did this, I'm sure, was to look up the thermodynamic data on page A3 in your textbook, and then recall that any of these types of standard changes, be they entropy, enthalpy, or free energy — I chose enthalpy there, but you could replace that just as easily with an S or a G — is equal to the sum of the formation data of the products minus the reactants, each multiplied by their coefficient. And notice there is a coefficient there. So I hope you did those calculations. I hope you got your units correctly. I'll be checking for them, and we'll need them in part 2 of our calculations. Okay, let's go over the calculations since this is the real meat of today's experiment. The first thing we want to get is the change in entropy data for dissolving sodium nitrate. Now, at a minimum, it's going to be equal to, the minimum value will be equal to the change in the enthalpy over the temperature in Kelvin. This comes out of the fact that delta G equals delta H minus T delta S, and since we know this is a spontaneous process and delta G will be negative, we can derive this. So fine, all we need are these two numbers, and one of them we got directly. It's just the initial calorimeter value in Kelvin. I should point out that in terms of the experiment, we'll be simply taking some of the sodium nitrate, grinding it up in a mortar and pestle, and then putting it in a calorimeter to measure the change in temperature. So there's your initial temperature there. Delta H we can get in turn from the change in temperature. The heat evolved, which is little q, well, be careful to differentiate little q, which is heat, from large Q, which is the reaction quotient. The heat evolved is equal to the mass of the solution, note that is both the water and the sodium nitrate that you added, times the specific heat of the solution, and that's very close to simply the value for water, so we'll use the value for water for that, times the change in temperature, and you don't have to bother converting that to Kelvin, or you could, you'll just get the same number. And that gives you the heat evolved, or required, in joules per gram degree Celsius. We'd like it to convert that to moles, joules per mole, and that's how we go from the heat evolved in Q to the enthalpy change, which is the heat at constant pressure, in joules per mole. So simply go from joules per gram to joules per mole, and you will get the delta H value. Now you enter them both, and you've got your change in entropy. So that's how we do the first calculation. I hope that's straightforward. In the second experiment, we'll take some calcium chloride, not sodium nitrate, but calcium chloride, and we'll dissolve that in water. We'll gather the same data, basically the change in temperature, noting the initial temperature. And now this time we want to get the reaction quotient Q. Here's the formula that we'll ultimately be using. There's Q right there. So let's think about what we need. We need the standard free energy change. Aha, we've calculated that in our pre-lab right there. Good. We need the measured free energy change. I'll get to that in a minute. We need R. Oh, R is easy. It's just a number. We need T. That's, once again, the initial calorimeter temperature. That's easy. And then we can solve for the natural log of Q. One good way to make sure that you're getting Q correctly is once you have everything, check your numbers, multiply it through, multiply this minus that times the natural log of the number you calculated. Make sure it all fits. Okay, the only thing that we have to do a calculation for is to find the measured change in free energy. That's done using the free energy formula, delta G equals delta H minus T delta S. So let's see if we have each of those pieces of data. Delta H, well, that we'll have to actually calculate just like we did before here. See how we got a delta H for this? Do the same thing to get a delta H for your calcium chloride. Fine. The temperature is once again the initial calorimeter temperature, so I guess we better measure that pretty precisely since we seem to be using that over and over again. And delta S, we calculated that in the pre-lab. We'll use the standard value right there. That gives you delta G. Now you have everything, and you can calculate Q. Okay, that's the second calculation. So that's the two big calculations. Make sure you do them before you leave the lab this evening. The summarized procedure is shown here. Take some sodium nitrate, grind it up, measure the change in temperature when it dissolves using a calorimeter. This involves using logger pro. This involves getting 3 calculations. Fine. Now, for the second part, we'll do the same thing for calcium chloride. Important note, and this is a modification to the procedure in your book. Don't grind it up. Just use it as it is. And we'll get the same data. Some notes. Both of these solids are spherical in nature, so don't try to weigh them on weighing paper or you'll end up with little ball bearings all over the place because that's what they act like. So be aware that the solids are spherical. Use a weighing boat. Do all your math before leaving. I'll go over it in a minute. And when you do the change in temperature experiment using Logger Pro, be sure to start the data collection before you add your solid. I do want 2 graphs. One of the temperature change that'll look something like this for the that should be sodium nitrate, and one for the calcium chloride as well. Whether it goes down or up, you'll have to determine experimentally. In either case, you can omit the supercooling, or I suppose it would be superheating region when you get your delta T. In other words, if it goes beyond the value and then flattens out, it's that flattened out data that you want. In this case, they would call this the supercooling region right there that you will be omitting. We did an experiment where we omitted a region like that before, but I believe it was a melting process. In any event, that's what you need to do. Okay, so 2 graphs. And the calculations, please number them 1 through 11, and here they are. The first 2 are pre-lab data. The change in entropy, under standard conditions for calcium chloride from your pre-lab. There it is up there. Show me that calculation. Same thing for the change in free energy for calcium chloride. You already calculated that up here. And let's get 4 pieces of data for the sodium nitrate experiment. I should say perform 4 calculations for the sodium nitrate experiment. 1, how much heat is evolved in joules per gram or required. How much enthalpy change it is. That's simply a matter of going from joules per gram to joules per mole. I believe the molecular weight is about 85, but check me on that for sodium nitrate. And then the change in the entropy value in joules per mole for each trial. And that's shown right here, how to calculate it. And take the average for me. For calcium chloride, let's do 5 calculations. 1, the heat evolved, just like we did for sodium nitrate, in joules per gram. Convert it to joules per mole using the molecular weight of calcium chloride. Give me the change in free energy using this calculation here. And then finally, what we were shooting for, give me the reaction quotient Q for each trial, and then take the average. In terms of safety for this lab, like all labs, be sure to use real goggles, not just the glasses kind. No shorts, please. Real shoes, even though it's starting to get warm. And this is experiment number 10, entropy, Gibbs free energy, and the reaction quotient.